Okay, so today will be very unusual lecture, and it is about functional programming. And by the way, talking about unusual, I was thinking about topics for next lectures because we were doing this already for more than a year, and we did a lot of data science, machine learning, and data architecture. And I did one lecture. Oh, what's going on? I don't even know how to turn it off. Okay, and we did one lecture on cryptocurrency, and I want to expand that. I want to do more lectures on cryptocurrency, but this is just a side note. Okay, so about functional programming. So first, I want to show what it is. So we have regular programming, which also called imperative, where you prescribe the steps and go step by step. Like for example, here we calculate factorial going step by step. We have variable I, which as we go through the for loop is changing, right, from 1 to n. And this is the typical imperative programming. And now I want you to look at something else. Like for example, here, this is factorial in Erlang. Erlang is a functional language. And this is factorial in Lisp. And this is factorial in Haskell. And you see how it's done? We define a function. So we say factorial from 0 is 1. Factorial for n, when n is greater than 0, is n times factorial of n minus 1. So we declare the rules. And then when we say factorial of 4, Erlang by itself says, okay, 4, we go here, 4 times factorial of 3, factorial 3 will be 3 times factorial of 2, and so on. So it will recursively do the calculation, right? Same in Haskell. Haskell is probably like the main functional language, the favorite. It's strictly functional. So we declare a function for factorial, call it FAC. And again, we say for 0 it is 1, for n it is n times factorial of n minus 1. And then we say print factorial of 5. Dollar here is just syntactic sugar. We will not go into that. Here's another example, factorial in Lisp. Lisp is a very old language. It's called Lisp processor. It was created in 1958. I was born in 1958, so I'm 64 years old. It's an ancient language. It's almost as old as Fortran. I think Fortran was in 1957. So it was before transistors. It was before chips. And here we define function called factorial of number n. And we say if n equal 1, look how it is expressed. First equal, and then n, and then 1. So this means equal n and 1, right? And then we return 1. Otherwise, we multiply n by factorial minus n1. That means n minus 1. Somebody is not muted. Please mute yourself. Okay, and then we call factorial 4, and it will calculate and it will give output 24, right? So you see, all functional languages, you declare the function, you declare the algorithm, you declare what needs to be done, and then language somehow does this calculation. Maybe slow, but you don't prescribe individual steps. So functional programming is declarative, as opposed to imperative step by step. Programs are created by evaluating sequential functions rather than setting values of some variables. Recursion is very common, used instead of for loops or while loops. Pure functions. Pure function is simply a function which has input and output, and you can predictably know the output if you know the input. So function doesn't depend on anything else. There is no randomness, there is no side effects. Side effects may be some global variables which could have changed, or date or time or temperature, or anything else. So pure functions are pure. So given the same input, they will always provide the same output. And in functional language, in pure functional language, you are using pure functions. Now, functions can be composed into sequences, passed as arguments, returned, saved, and when all your code consists of functions, this caused a very highly modular code, which is easy to debug. And because functions are pure, it's very easy to debug function by itself, right? So everything is good about functional programming. In Python, you can write here in an imperative prescriptive way, but you can also write in a functional way, right? So here we make a function to multiply two variables, then we calculate factorial as composition of functions, reduce function and multiply function. Reduce comes from this module. So again, there is no for loop, right? It's only function. So this is a functional style. Here is example of towers of Hanoi. It's a very famous problem. So you have three rods and you have set of disks stacked on the first one, so that the largest is on the bottom, the smallest on the top. And the goal of the game is to move the disks to the target rod one by one. You always take from the top, and you cannot put a bigger disk on top of the smaller one. So for example, if you want to move only one, you just move it, right? If you want to put 1 and 2, you can put 1 on the middle rod, then 2 on the target, and then 1 on top of the target, and you're done with 2. With 3, it's more convoluted. So here there is a step by step what you do with 3. With 4, with 5, it becomes really, really difficult to even imagine all the steps. And if you try to prescribe it, like using for loops, you cannot solve it. But you can express it using recursive approach, using functional approach. So you define a function called Hanoi, and then it calls itself. And you see that if it receives n, which is number of disks, then it calls n minus 1. So it's kind of like factorial. And these go in different order, as you see. So this thing actually works. and it's really amazing how some problems, like, for example, Tower of Hanoi, very easily and very elegantly can be solved using functions, but cannot be really solved using prescriptive imperative approach. Another shining example is a success story of Perl 6. I used to program in Perl, and Perl was created by Larry Wall, who was a linguist. And he was trying to make the language human. And the same word, the same expression in the language has different meaning depending on the context. And same in Perl, and especially in Perl 6. And people tried to make a parser for Perl 6, and they were failing over and over again. And then Andrew Tang, he later changed his sex and became Audrey Tang. He is a celebrity. He is absolutely amazing, well, guy, girl, person. He is now a digital minister of Taiwan. So it's an extremely high position, very, very talented, amazing. And then back then he was a student, and he was reading the book. He was learning Haskell, and the book suggests implementing a toy language as an exercise. So he picked up Perl 6, and he managed to parse Perl 6 expressions. So he made a parser. Why it was possible? Because he used Haskell, and Haskell is fully functional. So you declare the rules, you describe the rules, and then language takes care of actually parsing. So this is amazing success. Okay, over the years there were many languages which were using a functional approach. Some of them are fully functional, some of them have some functional features. The first historically was Lisp, as I already mentioned, and there are multiple dialects of Lisp. You can go on Wikipedia, you will see how many. This is just few. I remember using Lisp inside Emacs. Emacs is a text editor, and you can customize and program your own functionality inside it using Lisp. Clojure, it's a dialect of Lisp on top of Java. Haskell, as I already mentioned, favorite language for functional programming. Erlang, another functional language used for concurrent systems, and it has its child called Elixir. I was actually helping somebody to write programs in Elixir and to do website. So these are two for concurrent systems when you need a massive parallelism, but doing some simple repetitive tasks. And Elm is yet another functional language which compiles to JavaScript. And then there are many more, like for example, F# or Camel, which actually was a language which was used to make a compiler for Rust. I'll be talking about Rust. It's I think if you want to do functional programming, don't use Haskell, use Rust. There's a reason for that. Scala, which is based on Java, JavaScript definitely has functional features. Not functional first, but uses because of asynchronous nature. With JavaScript, when you look at the code, sometimes it's difficult to understand when each function will be run. Will it be run when the page loads? Will it be run when something is happening on the page? Anyway, it's all function-driven and event-driven. Python, you already know you can use functional approach, but also object-oriented approach, also regular imperative approach. PHP, C++, Java. The thing with Python, yes, you can use it like functionally, but it doesn't prevent you from also using imperative. And okay, I'll talk about it a little bit later. Three styles of programming. So we have imperative, object-oriented, and functional. Well, imperative is kind of opposed to functional. Object-oriented, you can use imperative programming for methods in object-oriented, or you can use functional. So object-oriented is not part of this argument. It's somewhere to the side. Different people try to create trees, like categorizing different languages, and it's not really possible because for example, here it says parallel processing for Java, but you can have functional processing and heavily parallelized. So this tree is not really like valid. It's just one of many ways how people try to separate them. So imperative programming prescribes the order of operations. Functional programming declares what needs to be done, but actual execution language does it for you. You have no control over it. Object-oriented programming brings data together with methods. Functional programming says that data and behavior are distinctly different things and should be kept separately. So completely different approaches. Real projects can benefit from using all three approaches. Also, you need to take into account maintenance and how you expect the requirements to evolve. So in practice, rigid object-oriented approach doesn't work very well, or rigid functional programming also doesn't work very well. Okay, a little bit of history. Lambda calculus versus Turing machine. Lambda calculus was invented by Alonzo Church. He was American, and it was in 1930. And Turing, Alan Turing machine, it's 1936. In Turing machine, it's a very, very simple abstract machine where you have this infinite tape, which is divided into cells. And on each cell, you may have symbols and values, and machine reads them, and then it goes to the table where for each symbol, it tells you what to do, and then it does it. It may write something, and it can move left or right, and then repeat. it's a very, very primitive machine, but it can be proven that this machine can actually do everything the modern computers can do, although very inefficiently. And lambda calculus also can do the same thing. Lambda calculus is Turing complete. That means that it can do the same things that Turing machine can do, but it goes from functions. So in lambda calculus, you have terms, t, and each term may be either a variable or it may be a function called abstraction. So it's a lambda. Lambda of variable x gives you t. So this is abstraction. And then you have application of those functions. So you apply this function to this, and this may be a variable or it may be another function. So this is lambda calculus, and you can express everything in it. Here, for example, this long formula, this is factorial expressed in lambda, in lambda calculus, not readable at all. So you can follow this link. I posted it on GitHub, and and see for yourself explanation of this formula. So history of functional programming, it all started in 1930, and then Alan Turing in 1936-37, and then Lisp in 58, and then Haskell in 1987, right? So Haskell was named after Haskell Curry. So this is a logician, mathematician. Okay, and this is how lambda looks, and this is how like factorial and Lisp again. I just put it here. Okay, a little bit more about functional programming. I already mentioned things, but I want to repeat and clarify them. So first, pure functions. Pure functions convert input to output, and the output depends only on the input, no side effects. Function composition. So you can execute many pure single-purpose functions, and you can string them together. Easy debugging, because pure functions are predictable and easy to test. Modular, because pure functions naturally split code into steps and modules. Clean code, very easy to read. Referential transparency, any function output can be replaced with its value. So if you already calculated function output for particular input, next time you get the same input, you don't have to calculate. You can just use the output, which you can save after the first application. So this can help you to optimize your code for speed. Lazy evaluation. So it can reuse results from previous steps. It doesn't do calculation until the point when it actually needs the value. Immutable variables. This is really strange. So it helps to make parallel programming reliable. So the idea is that once you create the variable, you cannot change its value. And if when you pass it, you basically pass the copy. And if you have, let's say, 100 processes running in parallel, they all get copies. They all can change something inside itself, but it cannot override things outside. So there is no shared memory. And this makes parallel execution very reliable. No while loops, no for loops. Instead, use maps, filter, reduce, and so on. Functional composition. So you can string functions together. So this is an example. So function goes from input to output, and then output is fed into another function, which is fed into another function. Currying. Currying, it's a case where you want to reduce the number of parameters you want to use. So it's transformation of a function with multiple arguments into a sequence of single argument functions. I'll show you examples later. Recursion, when function is calling itself. First class functions, meaning that functions are treated like other variables. You can pass them around. Higher order functions, this is basically functional composition. You can accept other functions as parameters or return functions as output. Monads, this is difficult, and I will not be able to explain it here. But basically, if you have one function which has output and you want to feed this output into another function, you may have situations where in the middle, like in the center of this composition, you want to do something. For example, you want to convert the type. So, for example, the first function returns integer and the second needs float, or vice versa. Or you want to write something into a log file or in a database, or you want to check for an error or for a null or something. So you want to do something in the middle. And this is done using monads. In Haskell, all input output, all file operations, database operations, like error processing, everything is done in monads. So you have pure functional code and then you have monads. So monads is where the code relates to real life, to external world. Okay, so here's some things explained or demonstrated. So for example, recursion. So you have a function myCount, and it calls itself inside this function. So this is example of recursion. Carrying. So here you're calling the function with argument a, and internally it creates a function which does a plus b. We're returning this function. So when you're calling function f, you give it 3, it will return function g, and then we give this g, we give it parameter 4, so it will calculate the sum, and it will return 7. So this is example of carrying. Closure, an inner function that has access to the outer enclosing function variables. So closures are similar to lambda functions. We'll talk more about them when we talk about Rust. Lazy evaluation. Expressions are not evaluated when they're bound to variables, but the evaluation is deferred until the results are needed by other computations. So this allows to make calculations faster by not doing unnecessary calculations. Immutability, very important part. So you do not change values of variables. Variables are immutable. Again, it's very strange because in regular imperative programming, you always set and change, update the values, but you don't do it in functional programming. You do not change state of anything. Everything is immutable. You avoid mutable data and side effects, dependence of global external data, file network, I/O, and so on. All these things are put in monads and in Haskell. So in imperative language, you can reassign the value A, give it B, and then change it to C. In functional language, the same syntax would have different meaning. You declare a variable A, assign B to it, and then you declare another variable and you assign C to it. So it's become a different variable. In some languages, you can add the word mutable or mute, and that actually allows you to set the values. But syntax is different. So you explicitly do it, you know what you're doing. So immutability is not always the answer. So suppose you need to process a huge pandas data frame, which takes gigabytes. And if you pass this data frame from function to function to function, every time you're making a copy of it, you will run out of memory. So this is not practical. So immutability, it makes it easier to write bug-free code, makes it easier to debug, makes it easier to write thread-safe code, and allows compiler to make very aggressive optimizations and make the code run faster. Okay, a little bit more. So for debugging, okay, side effects to avoid, tree function, functor, stream, monads. Well, I already spoke about monads. Oh, yeah, monads in philosophy. You see, it's like something very basic, like our life consists of monads. It's like atoms of something, and they may be mechanical or physical or spiritual, like so this existed for like thousands of years, the term. And then category theory. Well, this is recently, I don't know, last 30 years maybe. And again, we will not go into category theory. Frankly, I don't know it, but here is the link. Oops. Monad and functional programming. So I already explained what it is. They help to turn complicated sequences of functions into 16 pipelines, abstract away control flow, side effects, dealing with real world, and so on. Okay. Examples of good software that are written or is written, probably is written, using functional programming today. So there are multiple projects, but not as many as you would think. And there is a reason for that. And well, OCaml, remember Rust was written in OCaml, and Erlang, and a little bit of Haskell. He is the okay, Clojure, Scala, yeah, Erlang. Okay. More about the functional composition, monoid and monads. I guess I will not go through this, but it kind of shows you how you have a function G and F, and how you make a function which is composition of two functions and apply it to the argument X, and how H of G of F is same as this, so it's same as HG of F, so it's associativity. Monoids, it's mathematical, it's semigroups, whatever. We don't really need to know this. In Haskell, they take a lambda character and they remove the front leg, so it becomes a backslash. So this is lambda in Haskell. But anyway, I will just pass through this. And Haskell starter. If you want to learn Haskell, it's actually very easy. So this is, for example, the hello world in Haskell, just 2 lines. And you can compile it using this Glasgow Haskell compiler, and then you can just execute it. And it's very easy to install it. On Mac, you just do brew install this compiler. On Windows, just Google how to do it. It's easy. There is an interactive, like IPython, interactive Python. There is an interactive Haskell, so you can go there. It loads Prelude module, which talks to you. And for example, here I say print hello world, and it prints hello world, and I can quit. And this is excellent tutorial, 75 minutes. And you can go through it. Let's say it take you not 75 minutes, maybe a couple hours, but you will pretty much understand Haskell. Really great tutorial. And there are some other user guides and tutorials. Interesting thing about Haskell, it may run very, very fast. So sometimes it's only 5–10% slower than C, and sometimes people are surprised by that. And there are reasons for this. First, because it's compiled, not interpreted. There is no virtual machine. Everything is pure. Every static types is strongly typed. Lazy, doesn't do unnecessary calculations. But above all, being sufficiently high level that compiler can radically change the implementation without breaking your code expectations. What it means is that compiler, under the hood, it actually rewrites your code and makes immutable things mutable. So the language doesn't allow you to do this, but compiler can do it, and compiler can optimize the code tremendously. So there are many things you can do in Haskell. Everything you expect from regular language. You can generate random numbers. You can connect to databases. You can process data frames. You can create a server. Oh, this is Haskell. This is a functional golfing language implemented in Haskell. But the problem with Haskell is that the community is academic. They're not really creating a strong, like, production-ready tools. Things are buggy. They release new versions, and they're buggy. They're not really ready for production. So it's cool, but it's not really for production, unfortunately. And with the compiler also, you never know, like you never can guarantee, for example, the speed of execution. So sometimes it's very fast, like really 5–10% slower than C, but sometimes it's amazingly slow and you don't know why. And it's kind of annoying. So I got feedback from somebody who used it, and he said he will never use it on new projects simply because it was difficult, like all these things which I mentioned here. Another thing to mention about distributed systems is so-called actor model. So when you have parallel execution, so you have parallel workers, processes, they need to communicate somehow, but at the same time, you don't want them to override each other's shared memory. So how to handle it? And the answer is each actor gets a mailbox, and actors can communicate by sending messages into those mailboxes. And each mailbox is a queue, so it's a first in, first out, processing this queue. And it may be very effective, and this is a good model which people use. So there are books about it. There are some great presentations on YouTube. So if you think about parallel distributed processing, this is probably the way to go. Now I want to talk about Rust. And I really have only 2 slides left, and it's all about Rust. Rust, you see, according to Stack Overflow, 80,000 developers, Rust is the most beloved programming language, and it won the title 6 years in a row, which tells you something. So Rust is very pleasant language, very fast. It runs with the speed of C, and it has functional features so that you actually can use it as functional language 100%. It's very safe, it's bug-free, it's amazing language. So it was invented by Graydon Hoare, I'm not sure how to say it. And this is his LinkedIn, this is his GitHub. So he was originally at Red Hat, then he moved to Mozilla and he created Rust as his side project. Mozilla written in C, so it's millions of lines of code, maybe also C++, I'm not sure. And what you have a lot of bugs. And he wanted to make something which is more safe, more reliable. And the answer was Rust. So it makes code more reliable, it prevents segmentation faults, it guarantees threads safety, it's very fast, and it's open source, right? It first started as his own pet project, then Mozilla started investing millions of dollars and lots of developers and a huge community. And then he left and he moved to Apple. But anyway, very talented person. At Apple, he worked with the Swift programming language, and then later he works at Stellar, and this is related to distributed financial processing. So you can Google it up. So very interesting about the name of the language. So if you read this link, he explains it, and it comes from the name of the fungus, Rust fungi. So it's a plant disease which is over-engineered for survival, and this survival is achieved like the mechanism is more complex that you like would have imagined. So it's really interesting. I recommend to go and read this conversation. So Mozilla began sponsoring the project in 2009. Original compiler was written in OCaml. I already mentioned it's a functional language. Then it was shifted into LLVM-based compiler. And then it became like a compiler written in Rust. So it self-compiles itself. And it was like this for more than 10 years. And functional Rust, so pure functions, very easy to write them in Rust. Mutability. In Rust, variables are immutable by default. So it is like in Haskell. They are immutable. If you want to make them mutable, you have to explicitly like declare them as mutable. So it has a very strong control over immutability. Recursion, again, you can do recursion, you can use iterators, lazy evaluation, yes. Type inference compiler enforced. Type annotations on function parameters return values as required. generics type variables, traits, interfaces. So again, strong control over types. Function declarations in Rust are statements. They cannot be assigned to variables or used as arbitrary value, but we can bind the function to a variable, and then we can also use anonymous functions, closures, which is kind of like lambda functions, and put them into variables. So, and their declarations can be stored in variables, and then you don't need to annotate the types with them. Higher order functions. So this is example how you do something. You take 100 numbers, you multiply each number by 2, and you fold it starting from 0 value, and then for each element of the list, you add them together, right? So what you're doing here, you're calculating the sum of all the values times 2, right? So similar how you can do it in Haskell, whatever. So this is Rust syntax. Declarative style is definitely possible. This is actually example of declarative style. Carrying is also possible, but you need to be careful because Rust is routinely used for multi-threading, and it may interfere with memory safety when multi-threading. So you just need to be careful. So here are some examples. For example, closure. So here how you can do closure in Rust. Carrying, a way to reduce the number of parameters. Again, example how to do it. Binding. So here you have a function, and then you make variable and you bind it to a function, and then you can call this variable as a function, right? So this is like really functional way to do the programming. And this is example of towers of Hanoi. So same thing which I described before. You see, very, very simple. It actually works. I tested it. Okay, this is imperative. You can do for loop. And this is the same thing, declarative, right? So you do something, convert it into iterator, and then filter, take, collect. So function, call function, call function. Okay, these are some links. I highly recommend the tutorial by Derek Banas. I love his tutorials. It's only 47 minutes. I did it myself. Really, really recommend. Rust for machine learning. Rust is not ready for machine learning. There are some libraries, some tools, so you can do some processing, data frames, you can do linear regression and whatever, but you don't have tools like ready to use like you have in Python with scikit-learn, a variety of different tools to choose from. So, but it's going there, and eventually, maybe who knows, several years from now, it will be ready. It can be used for data processing. It can do it with the speed of C, very fast. So people do that. Okay, I guess this is it. I will stop recording.